Good morning, everyone. I am honored to present our research today at ICACT 2026. Our paper is titled A Hybrid Approach to Phishing URL Detection Using Bidirectional LSTM and Evolutionary-Spider Wasp Optimization. Our team from Delhi Technological University has developed a framework that treats URL as temporal sequences to stay ahead of evolving threats. Now, to give you an overview of today's presentation, we will begin by discussing the motivation and challenges of modern phishing, followed by a brief literature review. We then dive into our core methodology, featuring four-phase feature selection and a hybrid evolutionary spider wasp optimization algorithm, before concluding with our results, comparison table, and real-world applications. Now, moving to the core motivation of our work, phishing is no longer just a nuisance, but a global crisis with over 5 million annual attacks and organizational costs surging to $15 million and reaching $401 million for major breaches. It is clear that traditional blacklists are failing. There is an urgent need for a robust framework to identify sophisticated URL threats before they reach the victim. Our research aims to bridge this crucial financial and security. While the global impact is clear, phishing remains a moving target. Static blacklists fail against modern obfuscation, and even standard deep learning models struggle with noisy features and manual tuning. Our hybrid approach addresses these hurdles by meeting three core needs. First, automatic extraction of deep sequential patterns. Second, optimized selection to eliminate noise. Third, high precision tuning of hyperparameters. We designed our framework to meet these challenges head on. Now, to ground our research, we utilize the ISCX URL 2016 benchmark featuring over 11,000 unique samples. Each URL is defined by diverse lexical and structural features such as length metrics and entropy. Crucially, the dataset is perfectly balanced with 5500 phishing and 5500 legitimate URLs. This ensures bias-free training and a fair environment to prove the effectiveness of our hybrid approach. Now, to contextualize our work, we reviewed the evolution from static blacklists to machine learning, where researchers like Sahingos and Sohaib established the effectiveness of algorithms like random forest. Recent deep learning advancements, such as Jishnu's Robert A. LSTM model, achieved 97.14% accuracy. However, most existing studies rely on fixed architectures. Our work builds on this by introducing hybrid evolutionary spider wasp optimization, which dynamically fine tunes deep learning to achieve even higher precision and robustness. Our framework introduces three technical breakthroughs. First, a multi-phase voting strategy that filters out noise to keep only the most discriminative features. Second, our novel hybrid evolutionary spider wasp optimization algorithm, which simultaneously optimizes features and SVM parameters for maximum efficiency. Finally, a BiLSTM architecture that captures the sequential DNA of a URL. Together, these create a high performance system capable of staying ahead of complex phishing threats. Now, before training, we perform meticulous pre-processing to ensure numerical integrity. First, we handled inconsistencies by replacing infinite values with not a number and discarding features with over 30% missing data. Next, we binary encoded our targets and applied Z-score normalization to standardize all numerical features. This rigorous cleaning ensures our models train on the most informative data, providing the foundation for a high accuracy. To distill the most discriminative features, we employ a multi-phase voting framework. We use mutual information to filter the top 70th percentile, recursive feature elimination to strip weak predictors, and model-based selection with 50 estimators to rank importance. These outputs are combined through a voting mechanism to ensure a highly relevant, non-redundant feature set. To finalize our features, we apply correlation-based pruning, removing any redundant variables with a coefficient above 0.8. All strategies are then synthesized through a majority voting mechanism where a feature must be selected by at least 3 out of 4 methods to be retained. Finally, our fallback mechanism guarantees stability. If the voting result is too sparse, the system automatically selects the top 20% of features. This ensures the BiLSTM receives only high quality and discriminative data. Next, we pass the selected features into a stacked BiLSTM architecture. This bidirectional approach captures temporal relationships from both ends of the URL sequence simultaneously. We have engineered a high capacity 160 unit first layer followed by an 80 unit second layer using layer normalization and dropout. Dropout is from 0.25 to 0.30 to prevent overfitting. Extracted features are processed through a 256 neuron dense layer, concluding with a sigmoid activated head. We utilize the ADAM optimizer with a learning rate of 0.0004 and early stopping to ensure the model generalizes to new threats. We now arrive at our core innovation, the hybrid evolutionary spider wasp optimization optimizer. Our objective is to jointly optimize the BiLSTM feature mask and SVM hyperparameters, specifically C, that is the penalty parameter, and gamma, that is the RBF kernel parameter. Over 100 iterations, we evaluate each solution fitness using the F1 score. This hybrid is powerful because it balances diversity and precision. Evolutionary optimization ensures global exploration, while spider wasp optimization provides localized refinement towards the elite solution. This dual layered approach achieves a level of precision that standard algorithms cannot reach. To understand the hybrid evolutionary spider wasp optimization's effectiveness, we look at three mathematical principles. Equation 1 represents the spider wasp optimization component, where features inherit the state of the elite solution with a time decaying probability. Equation 2 introduces evolutionary diversity using a dynamic mutation probability to maintain global exploration early on before stabilization. Finally, equation 3 defines our adaptive stochastic search applying Gaussian noise with an exponentially decaying standard deviation. This ensures broad hyperparameter tuning that becomes highly precise, allowing us to find a global optimum without getting trapped. Finally, we move to the specific parameter update rules for our SVM. Equations 4 and 5 define how we update the penalty parameter C and kernel parameter gamma. Each update combines the current value, a learning coefficient alpha directed towards the elite solution, and adaptive Gaussian noise. We use a clip function to keep these parameters within their optimal ranges, 0.1 to 50 for C and 0.0001 to 1 for gamma. This hybridization ensures we navigate complex solution spaces with global exploration while mathematically zeroing in on the global optimum. Algorithm 1 on the left details our multi-stage feature selection. It shows our four-phase approach where features must survive M1 filtering, RFE, and SFM. By using a majority voting mechanism, we ensure that the final set F asterisk is highly discriminative and lean. On the right, algorithm 2 outlines the hybrid evolutionary spider wasp optimization framework. This pseudocode illustrates how we concurrently optimize the feature mask and SVM hyperparameters over 100 iterations using the F1 score as a fitness metric. Step 12 highlights our elite solution mechanism which guides localized refinement. This balance of global exploration and local tuning derives our model's peak performance. Following 100 iterations, we move to classifier integration. We use the optimal feature mask and hyperparameters discovered by hybrid evolutionary spider wasp optimization to retrain a final SVM model with an RBF kernel. This ensures the classifier is perfectly tuned to the temporal patterns identified by the BiLSTM. Finally, we perform a rigorous evaluation on a 25% stratified holdout set. This separate, unseen data produces our final classification, phishing or legitimate, confirming the framework's readiness to handle real-world threats. Moving to our experimentation and results, these curves prove our model's learning efficiency. The accuracy graph shows a rapid climb, stabilizing near 97%, with the validation curve closely tracking the training curve. This confirms the framework generalizes exceptionally well without overfitting. Simultaneously, the loss curves show a steady synchronized decline. The smooth stabilization validates our early stopping mechanism, proving the model reaches peak predictive power without computational waste. Together, these results confirm a highly stable and reliable detection system. To further evaluate robustness, we analyze two critical diagnostic curves. On the left, our precision recall curve maintains high precision across nearly all recall values, achieving an average precision of 0.9772. This proves the classifier remains reliable without sacrificing accuracy to catch more threats. On the right, the ROC curve shows near ideal performance with an AOC of 0.9867. Its sharp ascent demonstrates an exceptional true positive rate paired with an extremely low false positive rate. Collectively, these results confirm superior discriminative power for real-world deployment. To conclude our qualitative analysis, we present the confusion matrix, providing a granular look at our model's performance. As illustrated, the framework correctly identified 1598 legitimate and 1585 phishing URLs. Most impressive for security application is the low error rate. We recorded only 42 false positives and 46 false positive negatives. The fact that the vast majority of predictions fall squarely on the diagonal confirms high accuracy with a minimal false alarm rate. The level of reliability is essential for an effective and trusted real-world detection system. To validate our research, we conducted a benchmark analysis against recent state-of-the-art models. As shown, our BiLSTM with hybrid evolutionary-spider wasp optimization framework outperforms existing methodologies across every key metric, while the Robert A. LSTM hybrid by Jishnu et al. Achieved 97.14% accuracy. Our approach reaches a superior 97.31%. We also maintain a significant lead over the models by Putri et al. And Irsan et al. Notably, our precision of 0.9742 and F1 score of 0.9730 are the highest in the cohort. This proves that our hybrid optimization creates a more balanced, high-performance system for critical cybersecurity tasks. To conclude, our framework offers three tangible, real-world applications. It provides real-time cyber defense for browsers and email gateways to block zero-day threats and financial fraud mitigation to protect institutions from costly credential theft. Furthermore, it is uniquely suited for critical infrastructure protection in IIoT environments like power grids. By combining deep temporal learning with high-speed optimization, we provide a scalable shield for tomorrow's digital infrastructure. To wrap up, we have bridged deep temporal learning with metaheuristic optimization. By combining our four-stage feature selection, BiLSTM network, and custom hybrid evolutionary spider wasp optimization algorithm, we achieve a peak accuracy of 97.31% and an ROC AUC of 0.9867. Moving forward, we plan to deploy this as a browser extension, expand support for multilingual URLs, and test against adversarial phishing to ensure long-term robustness. Our research is built upon foundational benchmarks, primarily the ISCX URL 2016 dataset, and these references establish the ground truth for our 11,000 unique samples and the core lexical features we utilize for training. Our second set of references include the recent state-of-the-art studies in deep learning and metaheuristic optimization. These works provided the baseline metrics against which we proved that superior 97.31% accuracy of our hybrid evolutionary optimization. This concludes the presentation and I am now open to any questions. Thank you.